All right, in the last video, we were starting to talk about solubility, how much material is dissolved in a given, or a solute is dissolved in a given amount of solvent. In this one, we need to talk about how temperature affects all of that. And this is something called a solubility curve. So what we plot, because chemists love graphs, I guess, is solubility on the y-axis, which is how many grams of solute per milliliter of solvent, grams per milliliter, versus temperature. And we're going to kind of just look at a generic one and kind of talk a little bit about what's happening here. Okay. So we talked about things being above the solubility limit. It turns out that at low temperatures, stuff doesn't dissolve as well because there's not enough energy to overcome those intermolecular forces of the solute and the solvent, like we saw at the beginning of the last video. But the higher the temperature, the more stuff you can dissolve. And it turns out that it's not a linear relationship. For most compounds, every compound has its own shape of curve. Most compounds look about like that. Okay, so what happens is, as you increase the temperature, you can dissolve more stuff. Seems pretty logical. Okay, and if you are below this line, you have an unsaturated solution. Okay, you have everything dissolved. And anything above this is saturated, which is why our definitions of saturated and unsaturated were above and below the solubility limit. This line is the solubility limit. It is, for any given temperature, how much you can dissolve before you start ending up with solids just floating at the bottom. Okay. So, the way this works is basically, I think I mentioned in my last video that my mom is not a chemist. I'm going to keep hounding on the idea that my mom is not a chemist, I guess. So this is why every time I go to a restaurant, which I know in COVID doesn't happen at all now, but every time I go to a restaurant with my mom, she orders iced tea. And she orders it unsweetened, and then she pours sugar packets in it, and then gets mad when it doesn't dissolve. It is literally explained by this curve. So sugar dissolves pretty well in water, which is, we can ignore the fact that it's tea. And so what's happening is, if you were at a reasonable temperature, you can get quite a bit of sugar to dissolve in there. But if you order iced tea and it's cold, the amount of sugar you can dissolve is very, very low, which is why the sugar particles just sit at the bottom. And my mom will get a spoon and she'll stir it around and crush those little sugar particles and hope that they dissolve, and they just never do. And she gets mad. And I tell her, I'm like, if you want your tea to be sweet, you have to order hot tea, or like sweet tea, where they added the sugar when it's hot, because if it's cold, you literally just can't make it dissolve. We have this argument every time we eat out together, which is why I've stopped having the argument. But this is the concept. I've literally drawn this graph at a Denny's before because it's not a complicated concept. So, but this allows you to decide how much stuff you can dissolve at a given temperature. It's a pretty easy, pretty useful piece of information. Solubility curves are really easy to come across. If you Google solubility curve, you can find almost any salt on there, okay, or any solvent. Okay, it depends on both salt and solvent. Okay, but what you find is that for most compounds, it's pretty straightforward, and it's based off that delta H thing. The higher the temperature, the more things you can dissolve, because you're overcoming the forces. You have more energy to actually make that happen. Okay, at low temperatures, you don't have the energy to overcome the solutes ripping apart and the solvents ripping apart to be able to mix them together. If they don't come apart, they can't mix. Okay. Yeah. This also leads to stuff, there's a few weird concepts I want to talk about. The first is something called a supersaturated solution. Okay. So a supersaturated solution is when you take a saturated solution, so something above the solubility limit where there's solid particles at the bottom, okay, and you heat it until it all dissolves. So I guess I'll pick a new color here. We'll go with green. Actually, let's go with red. Red's a little easier to see. Okay, so let's say you're up here. Okay, so this is this story up here. So let's say we have this concentration. What this means is we are cold enough that, yes, a little bit is dissolved, but most of this amount of solute is just sitting at the bottom or floating on the top or whatever, but it's not dissolved, okay? In theory, if you heated this up, you would cross this line and it would all dissolve. Great, okay? And then what you do is you very nicely and gently cool the solution. So slowly and gently cool the solution. And what happens is you will end up pretty much back where you started, except it'll all still be dissolved. Because if you have water molecules sticking to a chlorine or a sodium or whatever, if you cool this, they want to be separated because there isn't enough energy to overcome those particles or the intermolecular forces, but it takes energy to rip these things apart, okay? So what happens is you end up providing enough energy to make it dissolve, and as long as you cool it slowly and gently, there won't be enough residual energy around to rip them back apart. Okay, and what you do is you end up with a solution above the solubility limit that is dissolved. Okay, it's really unstable. Honestly, what happens is if you heat this up and then cool it back down, you'll end up with this stuff that really, really wants to have solid because it's really unhappy. It's way above this curve. And it takes almost no energy to pull these things apart and get them back to their solute and solvent separately. So honestly, this thing is so unstable that if you had a supersaturated solution and you flicked it, or if you breathe on it too hard, or if it's just warm in the room, if you're holding it in your hands, if there's any source of energy, it will actually make all the solid crystals just fall out real fast, and it kind of like rains out these solid crystals. It's kind of a cool little thing. It comes up a lot in organic chemistry, but I at least wanted you to get the concept. Okay. Speaking of organic chemistry, we can use this concept, the solubility idea, to purify impure crystals. Okay. This process is called recrystallization. Okay. So any of you who take organic chemistry, maybe mark this video as one of your favorites, because anytime you take organic chemistry lab, you're gonna have to do a recrystallization about every other week. And understanding how it works and why it works is really helpful. Okay, so what this is done, or why this is done, is this is used to purify crystals. So in other words, if you, I mean, it sounds like some hippie nonsense, but basically if you're in a lab and you're making a product, a lot of times it's a solid, some sort of crystal. Okay, if you make aspirin, it comes out of these like kind of weird white crystals. Okay, but it's entirely possible that they'll be impure. If you check the melting point, they just might not be right. Okay, so what you're trying to do during a recrystallization is you are trying to dissolve the impurities in the smallest amount of solvent possible, heated solvent, and then when you cool it back down, the hope is that the crystals will reform, but the impurities will stay dissolved. Okay, a little weird, but it works. It works really well, actually. Okay, so what you do is you dissolve the impure crystals in the smallest amount of heated solvent. Oops, amount of heated solvent. The reason we're using heated solvent is at high temperatures, it will dissolve more. So we want as high a temperature of solvent as you can get. Okay. And the hope is that when you put your crystals into this, both the crystals and the impurities will dissolve. Okay. Then what you do is once everything is dissolved, you're going to make this get cold fast. You're essentially going to try to do this, but you don't care if the crystals come back out. You actually want them to come back out. So what happens is you essentially heat this up, hope that the impurities stay dissolved, and then cool it back down. And you want to do it rapidly this time, so you put it in an ice bath. An ice bath is literally just water with ice in it. And what happens is the crystals, the purified crystals will reform, but the impurities will stay dissolved. I'm trying to write this up here. Hold on. But impurities will stay dissolved. Okay. There are a couple ways to cheat the system to ensure that you get your crystals back, but there is, if you ever take organic chemistry, there is literally going to be a moment of absolute sheer panic that you will experience multiple times during your, hopefully, couple semesters of organic chemistry if you have to take it, where you've been told, oh, you made a crystal, but it's impure, do a recrystallization. And what's going to happen is you're going to dissolve it, and it will dissolve just fine every time. That's not a problem. Getting your crystals to come back is the scary part. Because if you put it in an ice bath and your crystals don't reform, that means you've lost all your product. And you might have to start over. And you can't not purify it, and you can't reclaim these crystals. If they stay dissolved, you are destroyed, which is why you want to use the smallest amount of solvent possible. Okay? If you have too much solvent, it'll easily dissolve, but you won't get your crystals back. You want the absolute bare minimum, literally like heat up a solvent and then add it 1 drop at a time until your stuff all dissolves, and then stop. If you do that, when you cool it, you'll be just past that solubility curve. You won't be like way over here, you'll be like right here, and it won't take much to get back across this line. Okay, there are a couple tricks. Okay. So, a couple tricks you can do. The first is you can scratch the glass. This is just as horrifying as it sounds. What you do is you take, usually we do this in round bottom flasks, but you could use a beaker, it doesn't really matter. What you do is you take a glass rod, I'm going to use a pen, and what you do is you literally take the edge of the glass, and you don't want to snap it, so because it is glass, and you don't want to push through the bottom because it is also glass, but you want to push hard enough to scrape it and create, like, you know, like the line in my hand, you want to create a little texture. Okay? The scratch allows a jagged surface for the crystals to start reforming. If it's a smooth surface, they won't crystallize right. Okay? The jagged surface helps crystal formation. Brief story time. I remember my organic chemistry professor, my organic 2 chemistry professor, telling the story about how when he was in grad school, he had a favorite round bottom flask. You don't use these much in Chem 1 and Chem 2, but in organic chemistry, there's these flasks that are round. Okay, pretty common. They're part of glassware kits. They're pretty standard stuff. And he had used it for so many recrystallizations that the bottom was just scarred. He said you could barely see through it. But the beauty was there were so many jagged surfaces that it would basically recrystallize anything. It was kind of almost magic in that regard, because it just, no matter what type of crystals he was trying to regrow, it always had this beautiful surface for them to grow off of. And creating scratches helped that. And he told us that he literally broke down in tears in the middle of lab one day in his research lab because somebody walked by and put their backpack over their shoulder and swung by and knocked it over onto the floor and it shattered. Didn't even have anything in it. But he realized that he was going to have to start over and re-scratch the glass. And scratching glass is like this horrifying sound. So having to do with this over and over and over again is terrible. Sorry. Okay, so this is the most likely trick. The other option is to get it as cold as possible. So if your ice bath doesn't have enough ice, keep putting more ice in it. This is almost cheating. I guess I'll preface it by that. You can actually just add a seed crystal. So these crystals, one of the reasons that recrystallization may not happen is it struggles to find a place to form those crystals. Scratching the surface is an option, but honestly, if you get one crystal to form, the other crystals will happily form off of it. Okay, what you can do is basically form a seed crystal. Okay. There's a couple ways to do this. The most cheater way is if somebody else has some and you just take one little crystal of it and throw it in your stuff. If it's cold, it won't dissolve because it's below the temperature, and it'll give a place for the other crystals to form around, and all of a sudden your stuff will just like fall out of solution. But stealing somebody else's stuff to put it into your beaker is kind of cheating, and you can't always guarantee you're going to have that. Another option is if you have that glass beaker that you've been stirring stuff with and scratching the bottom, if you pull it out, there will be a solution on the end of it, and if you just let it evaporate, what will happen is the solvent will evaporate and you'll leave the crystals behind. Yes, the impurities will come back, but not all of them, just a little bit. But you'll get enough seed crystals that when you put that back into the round bottom flask, it will give it a surface to grow off of. Those ones are kind of almost cheating, but honestly, if you're in panic mode in the middle of an organic lab trying to like save your crystals you've spent 3 lab periods making, you might be willing to take this. Don't start with that. Start with this. And more importantly, start with the smallest amount of solvent. If you add too much solvent here, none of these tricks will work. You have to do this right. It is important. So if you ever take organic, look this video back up because this will save you. It will help you a whole lot. All right, good luck.